we talked about Cartesian and polar representations of complex numbers. And in this video, I'm going to work out a couple of examples. We're going to look at the Cartesian and polar representations of some complex numbers that you might commonly see. And just to give you a quick review, a complex number z can be written as a plus j times b or as r times e to the j theta, where r represents the magnitude of the complex number and theta represents the angle or the argument of the complex number. Now keep in mind that r is the magnitude of the complex number. So r always has to be positive. So when you try to write a complex number in polar form, you should write it such that r is positive. Okay. With that in mind, let's go through a few simple examples. Suppose we have the complex number z, which is 1 plus j times 0, which is just same as the real number 1. So clearly, this real number, this complex number is on the x-axis at a distance of 1 away from the origin, right? So if we were to write it in terms of polar form, r would be equal to the length of this, which is equal to 1. By the way, this circle is a circle of radius 1. Okay, so this is a circle of radius 1. And therefore, the polar representation for 1 is as 1 times e to the j times, what is the angle that this vector makes with the positive x-axis? That's just 0, right? So 1 plus j times 0 is simply 1 times e to the j 0. Well, that seems a little uninteresting, so let's look at a few other things. How about the complex number 0 plus j times 1? Well, this complex number is here on the Argand diagram, right? So this complex number also has unit magnitude, but the angle that it makes with the positive x-axis is pi over 2. So this angle is pi over 2. Therefore, the polar representation for this would be 1 times e to the j pi over 2. Now, you can find the polar representation by just plugging into the formula that we saw in the last class. So for example, you can simply set r to be equal to the square root of 0 squared plus 1 squared, and you would exactly get 1, and you can compute the angle as the tan inverse of 1 over 0, which is infinity, so the inverse tangent of infinity is pi over 2. You can apply those formulas, that would be fine. But what I'm trying to do in this video is to let you to think about this pictorially or geometrically without relying directly on the formula. Okay, I think that's a little more insightful. Okay, how about z equal to negative 1 plus j 0? So negative 1 plus j 0 is this point. So this vector is this vector. And what is the polar representation for this? Now, I've seen students make mistakes where they will write this as negative 1 times e to the j 0. Now, it's accurate that this is true, but this is not the polar representation for z because we want the magnitude to be positive. So what you want to do is to write it as 1 times what is the angle that this vector makes with the positive x-axis. Well, that makes an angle of 180 degrees or pi radians, right? So negative 1 is the same as e to the j pi. All right, I think keep that in mind. And in the same way, how about negative j? Well, negative j, the complex number negative j corresponds to this vector, which is at an angle of 3 pi over 2 in the positive direction or pi over 2 in the negative direction, and the magnitude is still 1. So this would be 1 times e to the j negative pi or e to the negative j pi. And that's how I'm going to write it in this class. But of course, this is also the same as e to the j 3 pi over 2. So both these are exactly the same. Okay. Let's take one more example. How about z is equal to, let's say, 1 plus j. So z equal to 1 plus j is a vector that lies here. The magnitude of this vector is going to be square root of 1 plus 1, which is square root of 2. And the angle that this vector makes with the positive x-axis, I'm going to give you just 1 minute for you to think about this. So before I write it, I urge you to think about this yourself. So that's going to be j times pi over 4. Okay, let's just do one last thing. Minus 1 plus j. Now you can see that the magnitude of this vector is still square root of 2. And the angle that this vector makes is pi over 2 plus pi over 4, which is e to the j 3 pi over 4. Okay. Indeed, you can compute this angle by taking tan inverse of 1 over negative 1. And then, of course, resolve the ambiguity of theta versus pi plus theta, realizing that this complex number is a vector in the second quadrant.